each layer provides services to layer above and layer below. This service provision should be transparent, so we can change to a different layers. That is theoretical thing. Over here, we can see ISO-OSI reference model that has 7 layers. Maybe they also told you that meantime, the guys from ISO-OSI were arguing and computing for nearly 15 years. Commercial internet came up with something easier, that is TCP/IP reference model, which has 4 layers, or depending on what textbook or what teacher you had, it may also have 5 layers. That corresponds to layers of ISO-OSI. So, as I mentioned, the reason behind reference model is to split computer network stack to parts where each layer is responsible for different functionality. So they've told you that physical layer is kind of the abstraction for a medium. It hides you the specific of each medium, either wireless or wired. You need a data link layer or a link layer if you would like to communicate with adjacent devices that are directly connected. In case that you need a communication that is more than 1 hop away, then you need internet layer with IP addresses or other addresses that are used over there. Then we have a transport layer that is delivering you services that are not covered by any layer below, which are usually reliable and unreliable data transfer, retransmission, congestion control, flow control, and this kind of stuff. And we have an application layer that is the kind of the network part of each application that somehow operates with the program that is installed on your computer, and using the application protocol, this program is interacting with other program on different systems. So how is this thing surviving the reality of nowadays internet? If we will start from the bottom, we can see that on physical layer, usually internet service providers are employing something called dense wavelength division multiplexing. So we are basically splitting the layer 1 into virtual physical layers. Right now, we cannot imagine any company that is not using virtual LANs in order to separate employees to different IP networks, because they are sharing same layer 2 infrastructure, same switches. Moreover, some of our ISPs are employing something called Q-in-Q, where they are basically putting multiple 802.1q tags in a row in a series. If we are concerned about the security, we can of course use IPsec. It's a really robust framework that is able to leverage any existing encryption and hash integration algorithm, but it is like a Swiss knife that weighs 6 kilos. That is something that you would not like to carry around in a backpack, and it is the pain in the ass to configure for the usual user. Hence, a lot of people are using TLS SSL that is as robust as IPsec, but all the configuration is automatically done using the web browser or using the application. Now things are getting more complicated if we have ISP that is using MPLS, which is kind of the layer 2.5 technology that is appending something between the link layer and the internet layer. And things are getting even more complicated if we take into account VPNs and different kinds of the tunneling, where we are basically repeating the internet header and replicating multiple layer 3 PDUs. There are, of course, some overlay network technologies, just like the Lisp or ILNS or OTP, that are able to tunnel something using transport protocol. And the last thing is that, of course, if we are a lazy developer, we can use HTTP as our data transport protocol to tunnel all kind of application through HTTP, because it is provided in every usual, let's say, socket implementation, and all firewalls has open HTTP ports 80 and 443. So this is the mess that we are right now living, and which caused some problems in the internet. Right now, IP version 4 is more than 35 years old. IP version 6 is more than 18 years old, and none of them are providing us the solutions for the problems of the internet that they are present in TCP/IP from the beginning. For instance, problem with the identity of device. Assume this smartphone that has 2 network interface cards. One is wireless using Wi-Fi, another one is cellular interconnection to your provider. Each one has different IP address. If you are trying to communicate with this device as another device that is on the internet, you cannot tell based on these IP addresses that these two addresses belong to a same device. This is the thing that is really cumbersome and is complicating thing when we are speaking about the multi-homing or about the identity of devices on the internet. Moreover, a lot of ISPs are speaking about default free zone growth because whenever we need to change internet service provider, usually we are facing the problem with renumbering. We need to go through all our devices and change IP addresses that are on routers and computers. Of course, we can buy provider-independent addresses, but in that case we need BGP and to propagate our network towards backbone of the internet, thus increasing the number of networks that there exist on the backbone of the internet. As we can see, the trend seems scary, but we should take into account that this graph started in 1994. So it is kind of the exponential, but recent researches show that it is more linear than exponential. If I'm speaking about IP version 6, yeah, of course we can see exponential growth, but we need to compare absolute numbers, where over here we have around 30,000 networks, comparing to IP version 4, where we have around 600,000 networks. So that is an achievement for a 16-year-old network protocol like IP version 6. So, what is this recursive InterNetwork architecture? Basically, the main idea behind it is that instead of this rigid functionality that is delivered by each layer of network protocol, we have only one generic layer with programmable functionality. Moreover, we can take this layer and recursively stack it in order to achieve, for instance, the tunneling or VPN or this kind of stuff. It is not about just saying that this one generic layer that is called DIF, Distributed Inter-Process Communication Facility, is the only one thing that is good about the RINA. There are other principles and technologies that are combined in order to make this clean slate architecture that is not dependent on any TCP/IP stack part so good. Among of them is, for instance, that it is using data transfer protocol that is soft state and based on the timer synchronization. It is using complete addressing and naming scheme. It splits mechanisms and policies, and it is using single generic application protocol. I will be speaking about those four in few slides. If I should tell you something about the history of this RINA, it is quite a new thing. In 2007, the guy over here, the guy called John Day, which is formerly a chairman of ISO-OC and author of some of the RFCs, wrote a book, Patterns in a Network Architecture, A Return to Fundamentals, where he somehow pointed out the things that are repeating in each layer and that should be eradicated. For instance, take into account, let's say, Ethernet header. Over there we have a checksum. In IP version 4 header, we have also checksum. In TCP header, we have also checksum. While there are 4 checksum calculations. And he tried to outline a clean slate architecture that is trying to solve all the pain points of the internet. This architecture, this RINA, is funded also, let's say, research and ongoing development of the RINA is funded by the 3 European grants, and we've been lucky to be a part of the consortium of this grant. And since that time, we are basically developing a whole new framework, simulation framework, that is able to provide researchers with a simulating tool that is able to provide their results and the test bed for playing with this RINA. So if I will briefly mention these 4 key components of the RINA. First one is soft state transport protocol. Okay, you can ask me, what is the difference between the soft state and the hard state? In hard state transport protocols, we need some explicit synchronization. For instance, in case of TCP, prior to communication, there is this three-way handshake, the arguing or negotiating about the sequence numbers. Before every communication using TCP, there is this three-way handshake. On the other hand, we have soft state transport protocols that are not using any kind of the explicit synchronization. They are able to synchronize themselves automatically. RINA is using something called Data Transfer Protocol, DTP, that is based on the work of Richard Watson from Lawrence Livermore Laboratories, and his work and his own transport protocol that is called Delta T. This delta T protocol has mathematical proof that it is able to deliver reliable and unreliable data transfer if and only if by using the timers that are bound, and it is using 3 timers. Maximum packet lifetime, let's say the maximum time when the packet can be in a network and it can traverse through a network. Retransmission timer, which is a timer that the sender is willing to retransmit some unacknowledged data. And acknowledgement timer, which defines some maximum delay between receiver receives the data and sends acknowledgement. Using the values of these 3 timers, we can compute this delta T. And if we guarantee that these 3 timers are bound and synchronized between communicating parties, then we do not need any hard state synchronization. Because of this, we can make an assumption that all connections exist all the time, which is bold claim because it would also mean that we need to maintain all state synchronization for all connections, possibly infinite number of them. But thanks to this delta T and thanks to this equation, we can forget any state for each connection after 2 or 3 delta T times. If there is no traffic, we do not need to maintain any state. This DTP is also using sequence numbers. Each PDU has a sequence number, and thanks to the sequence numbers, we can offer both reliable and unreliable data transfer. In case we want unreliable data transfer, we just not take into the account the value of sequence numbers. We just omitting them. Second key part of the RINA is complete addressing. I already mentioned you the problem when we have one device that is using more network interface card. Each network interface card has MAC address and IP address. Problem with nowadays internet is that IP address is identifying and naming the same thing as MAC address. It is identifying interface, not a node itself. Basically, we are missing a part in TCP/IP where is the address that should identify uniquely device that is on the internet, no matter which network interface card this device is using. 2 minutes, it will be longer. To avoid this, RINA is using complete addressing scheme where we have physical addresses that are naming point of attachment and also logical addresses. Moreover, addresses in RINA can be flexible in a way that we will use as long in a bit size address that as it is needed. We can imagine that when we are in local area network, there are only few hosts. Hence, we can use shorter addresses. On the other hand, when we are on the wide area network, we need larger address space. Third part is split between mechanism and policy. That is something that is very neat for the RINA. What is mechanism? Mechanism is some functionality of the layer that is fixed, just like error checking. We need error checking to discard, let's say, the packets or frames that are error prone. The policy is, let's say, the way how the mechanism is being enforced. If we are taking into account error checking, we can make this error checking using CRC, or we can use parity bits, or we can use other way how to prove that the frame was received without any errors. So by splitting this policy, something that is flexible, from something that is fixed, we can easily change the parts that are policies and reprogram the functionality of the layer so it will accommodate all our needs and all our use cases. The last part is Common Distributed Application Protocol, CDAP, which is protocol that basically replaces any application protocol with 6 basic messages that works above the objects just like file or just like data stream that is delivered by the application. And these messages are read, write, create, delete, start, stop. Using only these 6 primitive functions, we can emulate any kind of application protocol just like HTTP or just like other application protocols. It is using primitive request response scheme. So because of the response, we can also receive a feedback whether the operation was successful or not. In RINA, we have only 2 we have two types of nodes. One are hosts and points of the communication. Another one are routers, where depending on number of layers that the router is using, we can differentiate it between interior routers that are like a switch, let's say analogous to TCP/IP switch, interconnecting devices on one layer using n-1 layers, and border routers that have more than two ranks of diff. For this, we modeled different kind of nodes in OMNeT using what was over there. And the main component of each node is IPC process. IPCP process is, let's say, instantiation of the diff membership. If I'm a member of a diff, I'm using IPCP to deliver all the services that is provided by this one generic layer. Services that includes routing, that includes data transfer, that includes some quality of service, resource allocation, and so on. So, over here, live demo, so that I will prove you that basically it is doing something. So, in this demo, I will show you a simple scenario when we have two nodes interconnected through the switch. In case of RINA, there are two RINA hosts interconnected using interior router. Over there, we can see the highest simulation modules, and if I will just go through a detail of host A, we can see that it has some part that contains application and these orange boxes that are IPCPs. This IPCP is basically the generic layer that RINA is about, and as we can see, both IPCPs of this host are same. What I will show you is how the data transfer works in RINA. So at time t equals 10 starts the communication where host A would like to send some data to host B using our kind of the ping-like application. So basically, it will ask, it will look through available IPCPs, and it will discover if I want to communicate with host B, I should use this IPCP. Hence, it will bother IPCP and ask IPCP, please allocate me a flow through which I can send the data towards host B. When there is flow allocation happening in this IPCP realizes, okay, I'm not directly connected to host B, hence I need to deliver it to my adjacent neighbor, to which I will use the bottom IPCP. And over there, recursive allocation and recursive call for flow allocation will occur, where there is flow between this IPCP process and this IPCP process.
That sounds very interesting.
That sounds very interesting.
No. Is this available as open source?
Yes, definitely.
Available as open source? Awesome. Is it already?
It is already open.
That is cool. That is very cool.
I just hope you are not interrupting me. They're like, okay, and that is
That's
it.
exactly what I'm doing. I just want to ask if there are any questions up until now. Otherwise, you can talk the remaining minute just fine. But if there are any questions, I want to give you the opportunity to ask now.
Come on, there will be a coffee break, no? And it will be.
Okay, go ahead.
So
1 minute.
I will just fasten the simulation, and recursively the flow allocation will reach this IPCP. Over there, IPCP will ask the destination application, are you willing to accept the flow and start to communicate with host A? And if destination application is willing, then it will create gates between the application and send response that right now, okay, the flow is being allocated. The message about successful flow allocation will reach host A. And at time t15, there starts this ping-like application where we can see that blue bubbles are being exchanged between application process and IPCP, which is basically this ping. Yeah? They are kind of the pinging that host A and host B are exchanging ping-like messages. So this is at least a demonstration that our thing is doing actually something after the 1.5 years of development. And let me conclude my presentation with last 2 slides. And so basically, as I mentioned, through this 1.5 years, we've been pretty preoccupied with developing all of this RINASim, this whole framework for arena architecture, which means that we basically implement all the features that are delivered by TCP/IP stack. We needed to implement something that is doing data transfer, reliable, unreliable. We needed to implement routing protocols that are working in this arena architecture. We needed to implement something that is creating the flow between communicating devices, and also the protocols that is so generic that is pain in the ass to implement it, but that is able to really be efficient, because some of our colleagues already employed just this protocol on their solution, and they are receiving really good results, because this generic application protocol contains, for instance, map and reduce operations by design in it, so you can, with single message, you can target multiple devices and perform more things. And this is it. It is freely available right now on this GitHub repository. We will be thrilled if you will download it and try it, but I'm pretty sure that without the knowledge of the arena, it will be for you really hard, and you will just observe some bubbles being exchanged. So in case that you will be interested in arena, I cordially invite you to a 4th International Arena Workshop that will be held in April in 2016, and it will be hosted by our institution, so by my faculty. Moreover, during the, let's say, last years, I was coming over here to the workshop, OMNeT workshop, with a project that is called ANSA INET, where we are basically extending INET for some different wired technologies, just like different routing protocols. And so far, we are in the middle of migrating our current current protocols for EIGRP, LISP, VRRP, TRIL, and ISIS protocols towards INET 3, so I just hope that next year we will have a chance to present. It was successfully submitted to INET and probably accepted. That's it. Thank you very much for your attention.
Thank you.
If you have any questions...
No more advertisements.
I presume you have some questions, because if not, then I didn't done my job properly, because, come on, I basically tell you that TCP/IP is old, unfinished demo of the internet, and right now I'm presenting you something that is the future.
My job is to close the session.
Okay, thank you very much. Or there is a question, or okay, coffee, and during the coffee you can ask questions.
So you can combine everything.
Someone has said that in the past 25 years.
That this is the salvation of the internet? A lot of time, I presume. We are one of many. But as I mentioned, at least the thing that I'm presenting over here is working somehow, and it should convince you that things that are right now problems of the internet are solved in this thing. That's it. It's right now it's a simulation and a half-functioning Linux distribution. We shall see whether it will be deployed in industry, let's say 2 or 3 years. Thank you very much.